Students will define electric field strength E as a force per unit charge in newtons per coulomb. Electric force is given by Fe equals QE, and the lines of force are used to draw the field. Field between two parallel plates is described, and so on. Student will be able to define the electric field qualitatively as the region of space around a charge where a positive net charge experiences force. That's what we're going to cover today. I'm going to define the electric field for you. Diagram electric fields using lines of force with respect to positive net charge. In other words, you're going to draw them. You're going to draw electric fields. Define the electric field quantitatively as a force per unit charge. Use E equals F over Q and solve problems using the field concept. F equals Q times E, same idea. Solve problems for the motion of charge between parallel plates, where F net is equal to Fe plus Fg. Very similar to friction. Describe a simplified version of Millikan's experiment. That's the one that we used to do research on and spend about 3 days. Today, I'm just going to, or this time around, I'm just going to tell you all about it. I'll spend the whole day telling you about the Millikan project, or the Millikan experiment. You're going to have to bear with me. I'll try to make it as exciting as I can. And define the elementary charge and convert between elementary charge and coulomb. So there's quite a bit to cover there. And scientific notation is very big. So if you're still not clear on that, make sure you learn that in the next 12 days. Okay? Because you will be out by 10 if you continue to do it wrong. So make sure you ask. Please don't be afraid to ask. I got one more thing to hand out, and then we're going to begin. Okay, so I have lots of information for you today. Unfortunately, the next couple days are you going to be doing a lot of sitting and a lot of listening. Okay? Yeah, they're excited. Because I got to do this introductory stuff here, and I also have to do the Millikan stuff, which is going to be, like I said, a lot of listening. Okay, so let's begin. So electric fields and potential. Let me just make this just a little bit bigger. Just want to make it big. No? Oh, there we go. Okay, so electric fields and potential. I would suggest a highlighter, a pencil, a pen, what have you. I also recommend you put your phone on airplane mode so you're not distracted. Let's begin. The space around a strong magnet is different from how it would be if the magnet were not there. Put a paper clip in the space and you'll see the paper clip move. The space around a black hole is different from how it would be if the black hole were not there. Put yourself in that space and it will be the last thing that you do. Similarly, the space around a concentration of electric charge is different from how it would be if the charge were not there. If you walk by the charged dome of an electrostatic machine, a Van de Graaff generator, for example, you can sense the charge. Your hair on your body stands out just a tiny bit if you're more than a meter away, and more if you're closer. The space that surrounds each of these things, the magnet, black hole, and the electric charge is altered. This space is said to contain a force field. Key term, right? A force field. Now you may hear the term force field described in like Star Wars movies and that kind of thing. Force fields do exist. Okay? You are all currently in a force field right now. Which one? Earth's gravitational field. You're also in the Earth's magnetic field too, by the way. Yeah, right? Can you see it? Can you feel it? No, it's just that. Okay, but we're going to talk about electric fields. And the key idea here that they're going to keep hammering back is they're going to show you the similarities between electric fields, and gravitational fields. So the force field that surrounds a mass is a gravitational field. If you throw a ball into the air, it follows a curved path. Earlier chapters showed that it occurs because there is an interaction between the ball and the earth, between their centers of gravity to be exact. Their centers of gravity are quite far apart, so again, this is action at a distance. And we talked about this in the gravitational field unit, right? The tennis ball is attracted towards the center of the earth, even though the ball is not touching part of the earth, is it? Right? But it is touching the Earth's gravitational field. So that's what we call that. That ability to apply a force at a distance is called action at a distance, without touching. Action at a distance. The idea that things not in contact could exert forces on one another bothered Isaac Newton and many others. The concept of a force field eliminates this distance factor. The ball is in contact with the field all the time. We can say that the ball occurs because it interacts with the Earth's gravitational field. It's common to think of distant rockets and space probes as interacting with gravitational fields rather than with the mass of the Earth and other astronomical bodies that are responsible for the fields. So if you think about the Earth, right, and there is a gravitational field, and an object, maybe a ball, is thrown, and it's going to curve because it's in contact with the field. That's how these scientists sort of got around this idea of this action at a distance. Just as the space around the Earth and every other mass is filled with the gravitational field, the space around every electric charge is filled with an electric field. I wanted to highlight it, not electric field. And the electric field is some kind of aura that extends through space. In figure 33.2, a gravitational force holds a satellite in orbit about a planet. Where is that picture? Right here, right? Down here. In figure 33.2, a gravitational force holds a satellite in orbit about a planet, and an electrical force holds an electron in orbit about a proton. In both cases, there is no contact between the objects, and the forces are again acting at a distance. Putting this in terms of the field concept, we can say that the orbiting satellite and the electron interact with the force fields of the planet and the proton and are everywhere in contact with these fields. So once again, I can draw in the gravitational field, and similarly, I can draw in an electric field around this proton. Okay, so the electron is attracted to it, right? It's touching the field. What do you know about these kind of gravitational fields? What's one thing you can describe for me that you know about them? Like about the strength. Where is it strongest? Where the arrows are close together, like at the surface of the Earth, right? You think it's going to be the same thing over here? It's literally exactly the same thing. Okay? So this idea of the field is the same, which is why we do gravity first, because people can sort of relate to it. Makes sense to them. Now, an electric field has both a magnitude and direction. What does that mean? If something has a magnitude and a direction, well, that means that it's a vector. Remember those good old days when you thought you were done with vectors? You're not done with vectors. They are fundamental to physics.
They're not fun.
They're not a whole lot of fun.
Fundamental is bad.
Fundamental is a bad word? Why is that?
Lots of fundamental things are fun.
You're right. Like even in hockey, what are the fundamentals? Exactly, right? Are they fun to practice, just passing back and forth? Come on, no one likes practicing passing. Its magnitude or strength can be measured by its effect on charges located in the field. Imagine a small positive test charge. This idea of a test charge is important. Small positive test charge that is placed in an electric field. Where the force is greatest on the test charge, the field is strongest, and where the force on the test charge is weak, the field is small. So we can sort of measure gravitational fields by just using everyday objects, to measure electric fields, right? Everyday objects have mass, which is why they're affected by a gravitational field, but everyday objects aren't affected by electric fields because they have to have a charge to be affected, okay? So we use a positive test charge to test them. And where the force is greatest on the test charge, the field is strong, and where the force on the test charge is weak, the field is small. The direction of the electric field at any point, by convention, is the direction of the electrical force on a small positive test charge. So in other words, we always use positive tennis balls to check out electric fields. Always positive. Always, always, always. I don't always use the word always, but in this case, it's always. If you screw that up, guess what? Everything's wrong. It's kind of like messing up red, meaning stop at a driver's test. It's an automatic fail. Okay? Don't mess it up. Small, positive test charge. Thus, if the charge that sets up the field is positive, the field points away from that charge. If the charge that sets up the field is negative, the field points towards that charge. So you can easily get the direction wrong if you screw it up. Don't. Be sure to distinguish between the hypothetical small test charge and the charge that sets up the field. And I'm going to be talking more and more about this. I'll keep reviewing it and repeating it. The strength of an electric field is a measure of how great a force will be exerted on a small test charge placed in the field. The test charge must be small enough that it doesn't push the original charge around and thus alter the field we're trying to measure. If a test charge Q experiences a force F at some point in space, then the electric field E at that point is, and there, my friends, is the formula that you're going to be using. E equals F over Q. And I like to quantify the F with a little e in there. So the electric field strength, which is represented by the letter E, is equal to the force, the electric force, which is why we have the E, the electric force, divided by Q. And what do you think Q stands for? Charge. Q is charge. And it's a small q, by the way, too. And there's a set of notes coming up right away with this kind of stuff in as well. Electric field strength can be measured in units of newtons per coulomb. That's what we use for the units of field strength. Newtons per coulombs. Why? Because the electric field is measured in newtons and charge is measured in coulombs. The word is coulombs. Charles Coulomb, French, I believe. It's also equivalent to volts per meter, which we will never get to. Okay, so let's talk more about these electric field lines. Since an electric field has both a magnitude and direction, it is a vector quantity, can be represented by vectors. Now I'm going to explain a little bit. I showed you gravitational fields. I didn't really talk about the lines themselves. I'm going to explain that a little bit more right now. The negatively charged particle in figure 33-3 top, that's this one over here, is surrounded by vectors that point toward the particle. Okay, so we've got a negative charge right here. All of these lines here are just right in the side. They are vectors. Notice how far away, how long is the vector? Right up here. How long is that vector? It's pretty short, right? And then as you get closer, the lines get bigger and bigger and bigger, or longer, I guess I should say. Maybe not bigger, longer. Now, do these vectors show the strength at all points around this object? And the answer to that is no. They're only showing 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and so on, right? It's only showing the strength at that point. What's the strength over here? We don't know. If we wanted to show the strength there, we'd have to draw in another little vector, and another vector, and another one. And what about right there? Well, we'd need another one there, and another one there, and another one there. And what about right there? I'd need another one there, and another one there, and another one there. What about right there? I'd need another one there, and another one there, and another one there. And literally, I would get what? I would get a big, coloring book. A big blob of red, because every point in space would need to have its own vector. Again, these are vectors. Okay, so smart scientists said, well, that's not going to work, right? Why this charge here, I just need to erase a smidge. What's the original charge on this guy right here? negative, which is why all the vectors point towards, because what do I use for my test charge? Positive, so they're all attracted to it, right? If the particle were positively charged, all the vectors would point away from the particle. The vectors always point in the direction of the force that would act on a positive test charge. The magnitude of the field is indicated by the length of the vectors. The electric field is greater where the vectors are long than where the vectors are short. To represent a complete electric field by vectors, you would have to show a vector at every point in the space around the charge, like I tried to draw here. Such a diagram would be totally unreadable. It would be nothing but one mass of ink, regardless of what color it would be. Useless. A more useful way to describe an electric field is with electric field lines. Now, unfortunately, they look exactly the same as vectors. They're arrows, but I need you to understand that these are different. These ones are vectors up top. These ones down here are field lines. Now, there is one difference between the vectors that you see up here. Let me see if I can get rid of these guys. What's the difference between these guys up here and these guys down here? Say again? Yeah, there's three vectors. Some are short, some are long, right? They're varying lengths. These ones here are all the same length. Okay, do you see that difference? These are not vectors. These are field lines. Okay? Where the lines are farther apart, the field is weaker. So the length of it doesn't matter. What matters is how close it is to its neighbor. Okay? Where the lines are farther apart, the field is weaker. For an isolated charge, the lines extend to infinity. In other words, these field lines go forever. And really far away, way out here, the electric field is weak. And in down here, it is strong. Did I not ask you that question on the gravitational fields test? I did. Some of you didn't get it right. Some of you put strong and weak at exactly the same distance apart. Doesn't make sense to me. Okay? Where it's far away, it's weak. Right? Where the lines are far apart, it's weak, and where the lines are close together, it is strong. Okay. So these ones here are vectors. Make sure you understand the difference. These ones here are field lines. Okay, so where the lines are farther apart, the field is weaker. For an isolated charge, the lines extend to infinity. While for two or more opposite charges, the lines emanate from a positive charge and terminate on a negative. So look at these pictures here. Guys at the back, you need to watch. Colby. Way too much time visiting. Way too much time. These guys here, this is an isolated charge. This line will extend forever. But when you've got two charges, it goes from positive to negative, and it ends. Do you see how do you see the arrows here? How they go from positive to negative? Why do they go from positive to negative? Why? Well, because if I put a positive test charge right there, it would be pushed away from this guy, and then it would be attracted by this guy, right? The field is always the direction that a positive test charge would go. Okay? What is the strength right about there compared to, like, say, right about there? Would it be the same? Would those two blue dots have the same field strength there, or would they be different? Why would they be the same, Jason? Because the field lines are the same distance apart. You will notice that when you've got what's called, and I'm going to come back to this again, I'm just going to give you an introduction here. These are like plates, metal plates. One has a positive charge, one has a negative charge, and the field in between is what we call uniform. It's the same strength everywhere. How can you tell? Because the lines are the same distance apart. Is it uniform over here? No, because here it's farther apart as compared to down in the middle here where it's closer together. Okay, so plates give you this consistent field. Okay. Photographs of field patterns are shown in Figure 33.5. The photographs show bits of thread that are suspended in an oil bath surrounding charged conductors. The ends of the bits of thread are charged by induction and tend to line up end to end in the field lines, like iron filings in a magnetic field. Maybe in elementary school, maybe you had a teacher with a magnet, put a piece of paper on top of it, sprinkled some little iron bits on it. Do you guys ever see that kind of stuff? Yeah? Same idea. Okay? Notice that the plates, notice that between the plates, the threads are aligned parallel to each other. The field has a constant strength between the plates. Also notice the threads inside the cylinder are unaligned. There is no electric field in the space inside a conductor. The conductor shields the space from the field outside. So let's look at these pictures here. So this picture here in the top left, I realize it's sort of a photocopy, so it's kind of tough to see. But would these be opposite charges, or would these be the same charge? Like would these both be negative? Or would they both be positive? Or would they be one positive and one negative? A one of each? How can you tell? Because they connect exactly. Right? See how they connect like this? They look almost identical to that previous page, right? Can you tell which one of these is positive and which one is negative? How do you know, Jason? You'd have a 50-50 chance. You cannot tell. Because there's no arrows here, right? These are actual pictures. Okay? So it's only like scientists are they're going to describe the direction using that positive test charge. Do they have to use a positive test charge? Is it like a law of nature? No, it's a law of science. It's a prescribed one. It says you must, right? But it doesn't have to be that way. They could have chosen negative test charges. These ones here, are these opposites or are they equal? How do you know they're equal? Because they don't connect. In fact, they kind of go away like this, right? Okay? All of these are pictures of electric fields. What about this one here? Here we've got those plates again. Notice that inside, what do the lines look like? They're straight or parallel, we might say, which indicates the field strength is uniform or constant. It's the same throughout. Notice that on the end it kind of bends like this, right? Is there a field over on the outside over here? Is there a field here and here? There is indeed. So you need to draw that as well. It kind of bends here at the bottom. Okay? We're going to spend some more time on drawing things in a bit. Here we've got a charged plate and we've got a cylinder. Are they opposite charge or are they the same charge? They look like they're connected, don't they? Right? They're connected, so that means that they have opposite charges. Notice that inside there is no field. How can I say that there's no field? It's just kind of like there's no pattern, right? There's no lines. Just sort of all over the place. And I think there's a key at the bottom there that tells you the answers to those questions that I've just asked. Okay. If our only concern for electrical forces were limited to isolated point charges, the electric field concept would be of limited use. The force between point charges is adequately described by Coulomb's law. Coulomb's law is a grade 12 concept. Charges most often are spread out over a wide variety of surfaces. Charges also move. This motion is communicated to neighboring charges by changes in the electric field that emanate at the speed of light. As later chapters will show, the electric field is a storehouse of energy. The energy can be transported over long distances by an electric field, which can be directed through and guided by metal wires or directed through empty space. And that's how they transport power, like from way up north down south from the dams. Okay. One last thing here before I sort of move on a little bit. Question. Over there on the right-hand side. See that box on the right-hand side? Suppose a beam of electrons is produced at one end of a glass tube and lights up a phosphorus screen on the inner surface of the other end. When the beam is straight, it produces a spot of light on the middle of the screen. If the beam passes through the electric field of a pair of oppositely charged plates, it's deflected, say, to the left. If the charge on the plates were reversed, in which direction would the deflection occur? If you reverse the charges, change the direction of the electric field, what's going to happen to the electrons? They're not going to be deflected left, they're going to be deflected to the right. Who cares about that? Does anyone care Is there any use at all for this? Do we even know what they're talking about? You've totally lost me, Mr. Bennett. There's a glass screen here, and it's coated with phosphorus. And over here, we've got an electron gun that's shooting out negative electrons. And when these negative electrons touch the glass screen right there, they start to glow. Okay? And if you've got plates, say positive plate and a negatively charged plate down here, which direction is the electric field, by the way? From positive to negative. So we've got this electric field like this. Now if I were to somehow magically reverse the positives and the negatives on these plates, what would happen to this field? It would be reversed, right? Okay, now, if, let's say, we've got positive on the bottom here, these guys here, these guys are electrons, they're negative, so these electrons here are actually going to be, I'm just going to erase this, these electrons here are actually going to be bent inside the field, they're going to be bent down. And instead of this glass lighting up there, it's going to light up right there. Okay, I go back to my original question. Who cares? Well, about 25 years ago, or even, I guess even less, I had to stop asking this question about 15 years ago. I still ask the question, I just say it a little bit different. I used to say, who cares? And you guys would all say nobody. And then I'd say, no, you all care because you all have one of these in your home. Nowadays, you don't all have them in your home. You know what I'm talking about, Mallory? What am I talking about? No, not a plasma TV. No, but you're on the right track. You're very close. Those old school tube TVs. Who's got an old school big 32-inch big box TV in their basement? Yeah? You got one of these in. Oh yeah? I think I paid $1,000 for a 32-inch tube TV. Have you ever been? Have you ever just unplugged it while it's on?
Yeah, it goes, and the screen glows.
It glows, and then does it go down to a dot?
Oh.
When you unplug it, you are taking away the electric field, right? Because there's no more charge. And what happens to the electrons? They shoot straight on through, and they end up glowing right. Does it go to the center, Vinny? Yeah, that's exactly what it does. Okay. So how those old school TVs used to work was the electrical signals would come in and they would adjust this field very, very, very quickly, and that electron gun would go back and forth. It's called the refresh rate. It will go back and forth on the screen, right? And if you look really, really close, those tubes, what does yours look like if you look really, really close? What do you see right at the screen? Look at get like this far away. Now with that, you look really close. On there will be 3 dots, and they're the primary colors, which are
Red, green.
red, blue, green.
Red, blue, yellow.
I don't teach kindergarten, but I know that green is not a primary color. Red, yellow, blue, I think, right? Yes. The dots will be red, yellow, blue, because when the white light hits them, it hits them in certain proportions, and that's what creates the color. So it's happening really, 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 really fast. And the better tube TVs would have a higher refresh rate, which means the electron can shoot faster and faster. That's how those things work. So there is actually a use for these electric fields. Okay, I'm tired. Are you tired of listening to me?
Yeah.
I bet you are. I'm tired of talking to you. There's a whole lack of questions here. I know I've got a couple more things to hand out, which I think I might do today in preparation for tomorrow. I would recommend you do these questions. All the answers are in that handout that I just read. Okay? At the very least, you should read the question and go, oh yeah, okay, I know the answer. Okay? There's not really any point in me going through it because I've literally given you all the answers. So let me give you a few minutes to that. I'm going to hand something else out, and then I'll be back in a few minutes. Which I've been talking about here, this is basically the notes for this. I gave you the handout. I sort of went through the big long summary thing here. Okay, so this is the shortened down summary version. An electric field is similar to a gravitational field. A gravitational field is defined as the amount of force exerted upon a unit of mass, and we measure gravity in newtons per kilogram. And so on Earth here, it's 9.8 newtons per kilogram. And I'm showing again the similarities. Okay? As well, gravitational field exists around any object with mass. Large masses such as planets have a strong gravitational field. Around any charged object, you might want to highlight that. Charged object. There exists an electric field. And obviously, but I should probably say it to be clear, objects with a large charge have a strong electric field. These fields are shown by a series of arrows radiating inwards or outwards, and these are called lines of force, or as I said earlier, field lines, which you will have to draw. Guys, please, like you've got like the rest of lunch to visit. My goodness, don't you get sick of talking to each other?
No.
I sure wish you would for an hour. All I need is that much time, Vinny. Like, stop talking for 12 minutes. Okay, so there's an electric field. Notice that the lines go on forever, and in this case, they are pointing away. Note that the closer the lines are, the stronger the field is. The strength is dependent upon the distance, and the inverse square law applies here as well. Now, I've talked about this inverse square law. If you're 2 times as far, then what's the strength going to be? It's not a half, it's a quarter. Inverse squared, 2 squared. If you're 3 times as far, then the strength is going to be 1/9. If you're 4 times as far, that's a 4. You're 1/16 the strength. What if you're 2.5 times as far? How are you going to do that? 1/2.5 squared, whatever that is. Okay? That's what the inverse square law refers to. To show the direction of the field, we bring another smaller charge, a positive test charge nearby, and it will be repelled. Right? Because positives will push each other away. Okay? So if this guy here, this big object here has a big positive charge, this positive test charge will be pushed away, which is why all of these field lines point in what direction? Away. Don't mess that up. I can't stress this enough. Okay, there's going to be like about 8 marks on knowing that. If you get them all wrong, then you just got 0 out of 8. Don't do that. Get it right. Make sure it's right on your cheat sheet. Can't emphasize that enough. It's super easy if you get it right. Well, it's super easy to get it wrong too, right? But it's like true or false, either right or wrong. Don't screw it up. Objects with a positive charge have fields that point away. If we were to have a large negatively charged object, the positive test charge is attracted, and the field lines point in which direction? Towards. Big negative charge, towards. Okay? You guys have these already, right? Objects with a negative charge have fields that point towards them. This amount of attraction and repulsion can be used to indicate how strong an electric field is. The field strength is defined as the force the field exerts on a unit of charge. That's one of the outcomes. You need to know that the field strength is defined as the force the field exerts on some unit of charge. In gravity, it's the newtons per kilogram, the unit of mass. What is the unit of charge here? It's not kilograms. I said it earlier today. Almost coulombs. Coulombs is the unit of charge. Okay? And so we have this formula. E equals Fe over Q. The electric field strength is the force divided by the charge, Q. E is electric field intensity or strength measured in newtons per coulomb. Fe is the force measured in newtons. Q is the charge measured in coulombs. Now there's another unit of charge that we're going to be getting into tomorrow. For now, we're going to be just dealing with coulombs. Now, key point, put a star beside this one because I get kids that make this mistake every year. The intensity or strength of an electric field is the same for a positive charge as it is for a negative charge, only the direction is different. Okay? So in other words, if I go back here, oh, I got to go a long ways back. Well, I'll go forward. Okay? If I've got, oh, no, I went too far. If I've got a charge here, plus 10, and I've got a negative charge of minus 10, their field lines are going to look exactly the same, just different direction. Okay, that's what I mean. Okay, and positive is not stronger than negative, or vice versa. Okay, now if I'm not mistaken, I think I didn't copy the example, right? Okay, I would recommend you take that handout that I just gave you with the notes on it, flip it over, it's likely blank on the back, is it? Yeah. Excellent. Let's do these example questions. We got 8 minutes, so I'm going right to the bell. Question is, what is the electric field intensity? What are they asking you to solve for? Which letter? E. They're asking you to solve for E at a point where a positive charge, 2.4 times 10 to the minus 6, that's why we did scientific notation. So this is our Q value. We are solving for E, and this is our F. So you're going to write E equals F over Q. I say you're going to write E equals F over Q, and then you're going to plug in the numbers. And you're going to get 3.2 is our force. We're going to divide by 2.4 times 10 to the minus 6, and you should get 1.3 times 10 to the 6. Normally, I would get kids to do that on the calculator and check it. We probably have time for that. You need to be able to do that. Okay, I'm rushing here for the guys that are going to be away. You need to be able to do that. Okay? Normally, I spend time helping kids out with calculators. I'll leave that for tomorrow. Okay? I got one more example for you, and then I'll be done. I got 5 minutes. So I really got to hustle. Here's example number 2. This one's a little bit different. I got 3 minutes, so I got to hustle. Here we have an object of charge. That is our Q. It's in an electric field. That is our E. We are asked to solve for the force. You're going to write the same formula. E equals F over Q. Excuse me? E equals F over Q. But now you're going to have to solve for F. Right? It would look like this. E equals F over Q. The E value is 2 times 10 to the 4. The F is on top. You have to multiply. Here's where the scientific notation gets a little bit messy. Right? You got to be able to handle that on your calculator. That's the answer you should get. I'm just going to leave that up there. Tomorrow I'm going to talk about Millikan. You guys should watch the video when you're down there in Dallas when the weather gets lousy. Right? And I'm going to give you time to work on these type of problems as well. Okay?